Yeah, we'll continue with another local expert here from the Technion, Professor Yasha Grobman. Yasha is a full professor, the former dean of the Faculty of Architecture and Town Planning at the Technion and the head of T-Code Research Lab. His research focused on performance, environmental, computational architecture, and design. Yasha.
Thank you, I'll start by thank Jonathan, and Naga for the invitation. Great event. I'm sorry I'm teaching. I cannot feedback. And but half the figures and the earlier lecture were amazing. So thank you. It's funny that the guy was my PhD student, and we both kind of thought the same about when we decided what to do here, but of course from a different point of view. So what I decided to do, I use those guinea pigs and doing different kind of presentation. I take a lot of my project and I try to do a retrospective on them, trying to think of where simulation is now and where should we be headed in view of AI, of course. And I hope you like it. It's a boom boom presentation. So I'm not going deep inside any of my projects, but let's see. So yeah, so that's the question. And I'm going to go over 6 lines of presentation, 6 lines of research, and a conclusion at the end. So the first one, I'm arguing that some design question right now, because of the increase in computing power, do not need anything else but computer power and simulation. So you can do enumeration and you can get to real-time simulation. So basically, this was an experiment. We tried to ask ourselves, how should we use external shading in a building? What is the right one and what is the right way to operate it? Whether it should be standing constant or we just shift it once in a month or once in a year or once something else. And we decided at the end to do a model to simulate the entire year. And basically what you get is real-time decision making. So you don't need to do a simulation. Basically, you get something like that. I will not wait until the simulation go through, but you get all the data. You ask yourself, boom, yes. So no simulation anymore. The second one is a different one, is flow simulation. So it's not urban flow, although I have some ideas about urban flow. I asked myself a question. Since now we can generate complex building, should we use the building envelope to create insulation? And but the question is how much? How much will it contribute? And we did the research. The first thing that you need to know when you work with non-linear simulation, that you need to calibrate. Simulation tools are not really calibrated. So you need to do a physical experiment, check it, and then to check it against a simulation. And sorry, to check it. It doesn't go back. Here. To check it against simulation, and then only to start using simulation, then you can do this, hundreds of rounds of simulation, and get to results saying that this chance it's 20%, you can increase 20% the insulation of a building. Same thing about fluids. We ask ourselves, can you use breakwater or something else? Not only as breakwaters, can you simulate it? Can we design it with simulation? So of course, we start using all kinds of tools, and we use physical simulation of this and trying to calibrate it to a simulation tool. And in this case, it's a visual calibration because there's no way to calibrate it better than that. And then, of course, we did a lot of tests and get to some kind of ideas about how water behaves. a lot of surprises here because you can't expect that. It's too complex. At the end, this sort of things that you're surprised with. And at the end, we thought that we introduced the city of Tel Aviv, a new type of beach with geysers and all kinds of things. But the idea here is that this type of simulation is highly complex, and you cannot, as for now, use machine learning because you cannot generate enough data set to simulate this thing. But given the enough computer power, probably somewhere in the future you will be able. So basically, this is today is the limit. Now, if you look at structural design, we look at the notion of topological interlocking. So basically, how you can structurally simulate a discrete object. And yeah, so we're trying to create this kind of flat floors, either to serve as a floor or to be to save you the scaffolding. So basically, you can do that, put concrete on top of it, no need for scaffold, take the scaffolding out. But we were trying to see how much it takes, and we needed to basically invent our own simulation. We use Earth simulation for that because it's discrete elements, and you need to know how it works structurally. So we developed, of course, another calibration because nobody knows how the simulation works. And we tried to develop all kinds of different sets of topological interlocking to understand what is the right and what is the strongest performing one. And we reached some results about the type of form, the type of angles, which are not drawn here. Some surprises. This way it behaves like just going down, but if you use rectangles, it starts rotating, which was very surprising and interesting. Then we get some sort of ideas about which form works best. However, in this, I mean, if you think of future perspective about this sort of discrete element simulation, this is Michael building project by Michael Weitzman. By the way, if you think about this, this is again, right now it's impossible to simulate, it's too complex, discrete element, but in the future, if you will be able to do enough of those, you'll be able to simulate this element for each sort of shape. So here again, AI will solve everything. Okay, so another level of complexity. Give me 5 minutes. Another level of complexity. Human behavior. So human are expected creatures. Sometimes, not always. So this is a project by one of the faculty here in our previous team, Lita Kalai, who simulated human behavior in hospital. He was able to test all kinds of design scenario. We took the same idea together with Michael and Davide, and did this with a proposal to export. 1 second, please. So we look at how people would consume the building, and we did this sort of simulation to show that this building works fine. So again, if you think about those type of simulation, it goes back maybe to what Pete said. Yes, we can simulate people behavior, but we don't really able to simulate people. They're too complex. This thing, I think, is the limit of AI, because unless you know exactly how people will behave, or you can do very big generalization, you will not be able to do it in the near future. So this is one of the limits as I see it, but we can discuss it later. The next thing is even more complex. I have just one more. It's simulating humor and motion. And we sit in the space, we feel nice or not nice. If we take the ceiling a bit higher, how would we feel? Can we simulate? So we thought that this is important. We thought that architect can now simulate everything but human emotion. This is a very big gap, and we want to solve it, of course. So we try to develop a methodology to do that. We introduced some spaces, VR. We were looking simultaneously with all kinds of sensors and putting people in the beginning in this type of lab, Daphne's lab. And so anyway, I'll show them maybe the lab later. And looking at all these sensors together and trying to make some sense. Where these sensors correlate and what's the relation to people's speed. Okay, so and we get this sort of big data set, both about how people feel and also where people look at the space. Okay, and then so these images like that, and we get to some sort of conclusion, like designers versus no designers. Like when we start the first grade, you always teach about continuous or smooth surfaces versus tessellated surfaces, and there is a difference between design and non-designers' appreciation of those. So we can prove it now. This is the expert and non-expert. We give all kinds of spaces, and we get all kinds of other conclusions about how people feel in long and narrow spaces as opposed to wide spaces. But anyway, we prove that it's possible to empirically measure this thing. And then, of course, this is like a video of how people consume the space. Imagine that you will know as a designer when somebody enters a room where his or her eyes is looking and what she's looking first and last. I think this is very interesting data for designers. We have the data yet and now solving it. So this is this impression. So now the question is whether we can do AI on that. I think so. I think that if we do enough simulation of that, we can simulate and create a tool, a new type of tool to simulate human behavior in space. So basically imagine yourself, a designer, you have a simulation of light, and then you have a simulation of, oh, here people will not feel good, here people will feel good. Interesting. The last thing is we focus only on humans. There are other species out there. How do you simulate for other species? So this is one of our latest lines of research, and we are arguing that we can introduce multifunctional environments. So our building is not only our building, it's also other species building. So, and we did this within a big project called Ecolabs with many universities that you see up there. And the idea was to try to create a methodology and a simulation process for animals, for people, for plants, and also microbiome. Now, I'm not, this is the entire process, but I'm not going to go into because my PhD student who developed our simulation process is presenting the bachelor. So I'll give Surein the credit. He's an amazing person, amazing PhD, and you will enjoy it very much. I'm going to show just a tiny fraction of different thoughts on that. And the idea is, so we looked at what are the criteria, what are the KPI, and that's the work of Tanya, who's sitting here. Say hi, Tanya. So basically, what are the criteria for multi-species? And what is the preference? Who's first and who's last? And then how do you basically choose plants? There is an ethical issue here. Do you go for the ecocentric approach, which all the animals are the same, or you choose pathocentric approach, which animals that feel pain are more important? There is a issue here of choosing the animals. So basically what we started with just basic geometry salt distribution. We received a model that distributed all the plants and the animals. Ren will talk about this. Then we did all kinds of simulations, and we get to a point. However, now what we're doing, and that Suren is not going to talk about it, that's a master student, Anastasia, sit here. Say hi, Anastasia. Now we're thinking about how we distribute this animal mobility. So probably the building will not be full of this. We should decide where and what is the priority. And there is no concrete solution. So simulation should give you all kinds of choices, but never a great idea. So this is, I think, an important point about simulation, because we usually are looking for a certain one good solution, which this type of research, there is none. You only can get all kinds of scenarios, you give them a score. This is where it's better for this species to be at the building. Other species, you can do set of criteria. But I think that in this research, it will be very, very difficult to use AI. And this until we understand who we design. That will take time because we used to design for people. We are already, how many, I don't know, considered the way it started. It's like 3,000 years designing for people, 5,000 years designing for people, never designed. So I think that would be a start, and AI here will be probably different. So conclusions, I don't have a great conclusion. I think we need to understand that the tools that we're using, there are simulation tools that help us and get the AI will get us immediate answers, like guide show and some of the ones I showed here. There are other types of simulation for flows mainly that are non-laminar flows that are very complex. We're not really there. So you cannot use statistical models to get to it. It will take some time, but probably will be there. But other types of simulation, like the one that involve human behavior and non-deterministic approach, or the one that involve what we call wicked problems, that thing will be left for designer to break their head with and invent new type of either simulation or evaluation, something that will be mixed. And the same thing about multi-species. Multi-species, I think that's what we need to do for the world, and we need to do it ourselves. Nobody will do it for us. No ML, nothing. So thank you. Thank you again.